You've already seen that we can use the properties of logarithms to make the process of taking derivatives of natural logarithms much easier, because we can break these natural logarithms down into simpler and simpler pieces. Well, it turns out we can also use that idea even when we don't have natural logs. So for example, here we have y is equal to x divided by the square root of x minus 4. So we have a quotient. The quotient has a square root in the bottom. That could be seen as a little bit of a mess. So let's start by taking natural logs on both sides. Let's think of this as the natural log of y is equal to the natural log of x divided by the square root of x minus 4. Now, of course, this only works as long as y is a positive value, so there are some kind of restrictions on this. We need to make sure that the x values we choose keep the right-hand side and therefore the left-hand side positive. But as long as that's true, we're okay here, and we can make use of this idea. So on the right-hand side, we can use the logarithm to simplify things. So we'll have the natural log of y is equal to the natural log of x minus the natural log of x minus 4 to the 1/2, where I'm rewriting the square root of x minus 4 as x minus 4 to the 1/2. And we can go one step further here. Natural log of y is equal to the natural log of x minus 1/2 times the natural log of x minus 4. Now, we can take derivatives of both sides of this. So we can consider d dx of the natural log of y is equal to d dx of the natural log of x minus 1/2 the natural log of x minus 4. And when we do the derivatives, what we have to be careful of is on the left-hand side we have an implicit derivative. We're taking the derivative of something that involves y with respect to x. We're going to need to remember back to what we did with implicit derivatives. And what we said was that the derivative of y is dy dx or y prime. So if I apply that idea and use the natural log of y, I'm going to end up with y prime divided by y, similar to the u prime divided by u we have when we say that u is a differentiable function of x. Well, what is y? Y is a differentiable function of x, so just a different name. So that's going to be equal to 1 over x minus 1/2 times 1 over x minus 4, which we could write as 1 over x minus 1 over 2 times x minus 4. And if we put that over a common denominator, we could think of that as 2 times x minus 4 minus x all over 2x times x minus 4. And if we simplify that a little bit, I'm going to bring this down here to this next level, we're going to end up with y prime over y is equal to, we're going to have a 2x and a minus x, we're going to end up with x minus 8 divided by 2x times x minus 4. And then what we need to do is we want to get y prime by itself. We don't care about y prime over y. We want just y prime. So we can multiply both sides by y. That will give me y prime is equal to x minus 8 divided by 2x times x minus 4y. And that gives us an implicit derivative, but we have an explicit rule for y. So we can say that y prime is equal to x minus 8 over 2x times x minus 4 times x over the square root of x minus 4. That will end up giving us x times x minus 8. And actually at that point these x's will cancel, so we're going to end up with just x minus 8 in the top. So let's do that. Divided by 2 times x minus 4 to the 3/2 power. And that works out fairly nicely. You could go through and take this derivative again using a quotient rule, and then whenever you take the derivative of the bottom you have a chain rule, and then you're going to have some algebra to do. You might want to do that to practice. We are getting close to the end of the semester, and you might see a problem like this on the final exam. And see if it does indeed work out to exactly the same value that we just found here, using logarithmic differentiation.